Okay, so we're now moving on from wave propagation. Don't forget any of that stuff. It might come in handy a little bit later, but we're going to do something else now.
Are we going to get our homework back?
You will.
Okay.
You will.
So we can look at it.
Yeah. We're going to now start talking about this part of it that we didn't really spend a whole lot of time on previously, which is we talked about amplitude of the wave, right? That when we start drawing these graphs of waves, the taller they are, that we call that amplitude. Amplitude usually correlates with how we perceive loudness. Okay, so typically higher amplitude, higher loudness. Here's the problem, though. If you try to figure out the difference in loudness between the loudest thing our ears can tolerate before they blow up and the quietest sound that they can perceive, the actual pressure, the actual air pressure that corresponds to those two extremes is a huge range. So the loudest sound that we can tolerate is 1 trillion times more than the quietest sound we can perceive. And 1 trillion is a really big number with a lot of zeros at the end of it. And I don't like to work with numbers that big. And neither do most people who do sound. So we've had to figure out a way to tame that range a little bit. Because what I don't want to do is say, oh, I need to turn this thing up by, 4,500. And that would get me to a little teeny difference, right? So I'd rather, develop some sort of shorthand. So that's what decibels are. Decibels are a shorthand. It's a unit of measurement that we've invented to help us sort of collapse this range of 0 to 1 trillion down to something typically in the range of 0 to 140 or so.
So it's a shorthand for amplitude?
It's well, yes, but it could be for other things too. Okay, it's really usually we use it in terms of loudness. Okay, but what it really does, as you'll see, is it really just tells you the difference between things. Okay, so we're going to first look at how we might use decibels to help us figure out power levels, because we sort of deal with sound in lots of different formats. It's not always air. Okay, a lot of times it's something electrical that's happening on a wire inside of a piece of equipment. And we can look at that electrical signal, otherwise known as audio. That's what audio is, right? Audio. The difference between sound and audio is the electrical representation of sound. Okay? Audio is sound that has been converted to some sort of electrical signal. Okay? So we can look at that electrical signal from lots of different angles, but one of the ways we can look at it is its power level. And there are some scenarios where looking at it as a power is beneficial, and there are other times when looking at it in terms of voltage is beneficial, and looking at it in terms of current is beneficial. And so for the moment, let's take a look at how we could use this when we're dealing with power, audio or sound as a power level. So power is usually measured in watts. And this term watts gets thrown around a lot in the audio community, sometimes in not particularly helpful ways, but as we'll discuss. But let's sort of just look at how we can take a very huge range of possible power levels that we could be dealing with. So here's just an example over here on the right of power levels ranging from 1 to 20,000. And 20,000 is a big number. Not quite as big as 1 trillion, but still more zeros than I typically like to deal with if I don't have to. So and if we sort of convert that into decibels, we get a range of 0 to 43. Now let me explain how that works. We use logarithms to do this. Okay? Now, I don't fully understand how logarithms work. I get that that it has something to do with the inverse of an exponential, and I kind of halfway understand what that means. But I can't manually calculate a logarithm. I don't know how to do that. And quite frankly, very few people really do. Because even before the days of having calculators that did this, most people that worked with logarithms, they would have a chart, right, that would just say, you know, logarithm of 3 is this, right? And so very few people actually calculate these things manually. So I would not waste a whole lot of brain energy trying to figure that out. For now, let's just assume that there's this thing called a logarithm, and it is a button that you push on your calculator, and it gives you a number that is smaller than the one you started with. Okay? So if you can just sort of accept that you push this button, and it gives you a smaller number. And that smaller number is somehow connected to the bigger number you started with. Okay? It is a smaller number that represents the bigger number.
And
okay?
What do you, I know we don't have to worry about like what it does or whatever, but what do you use the logarithm to figure out?
So what we're trying to do is we are trying to take this big, huge number of 20,000 and convert it into a smaller number that's easier for us to work with.
So that's
okay?
how you find
Yeah.
watts to decibels.
Yep. So essentially, the way we do this, and there's some steps involved, as you'll see, but we take this big number, we run it through this logarithm, and we get a smaller number, and then we can just use the smaller number, okay, to work with. Now, the way this works is there's a thing called a bell, okay, and you can calculate a bell by taking one power level divided by the other power level and finding the logarithm of that number. And that gives you a bell. The important thing to note here is that a bell, and consequently a decibel, doesn't necessarily represent an actual value. Okay? I mean, I am showing you a chart here where I am assigning actual values, but at the fundamental level, decibel tells you the difference between two things. Right? So in order to calculate a bell, you have to have two numbers to start with. You have to have one power level and another power level. And a bell, you know, when you convert that into a bell, it's telling you the difference between those two values using some smaller number than the actual linear difference, in other words. Okay? And when you collapse it down to a bell, it's still kind of too big of a number for us to deal with. And so a decibel is basically that value times 10. Okay? And it gives us a range that's a little bit easier to deal with. Okay? So a decibel is 10 times the logarithm of one power divided by another power. Okay? Before we do any of the math, let me just sort of explain some of the rules of thumb here. So when you're dealing with decibels at a power level, there's this thing that we like to call the 3 and 10 rule. And basically means that if you double a power, you get a 3 dB increase. And if you multiply a power by 10, that is a 10 dB increase.
Can you say that one more time?
So if you double a power, that is 3 dB difference. If you multiply a power by 10, that is a 10 dB difference. Okay? Now, it works the other way too. So if you divide a power in half, that is a 3 dB difference. It's just 3 dB less now. If you divide a power by 10, that's 10 dB less. Okay? So you can start to see, using that 3 and 10 rule, how using decibels allows us to collapse this huge range. So I've got a range here of 1 to 20,000. So I start with 1 watt, and I just arbitrarily say that 1 watt equals 0 dB. In other words, 1 watt is where I'm going to start from. Okay? And I can just decide that because it's my slide and my keynote thing, and I'm going to do that. Okay? So I can say that. So, and you have to do that because, remember, decibels only tell you the difference between things. So you have to figure out somewhere that you want to start before you can really deal with decibels, because decibel can only tell you the difference between where you started and where you ended up. Okay? So I am arbitrarily, somewhat arbitrarily, saying, well, I'm going to start with 0 dB, and I'm going to say that is equal to 1 watt. I have 1 watt, and I'm going to call that 0 decibels. So if I go from 1 watt to 10 watts, that's multiplying by 10, right? 1 times 10 is 10. So I've multiplied by 10, and therefore I get a 10 decibel increase. In other words, 10 watts would equal 10 decibels, or 10 decibels louder than 1 watt. Okay, is maybe the purer way to think about it. Now, if I take that 10 watts and say, okay, I'm going to multiply that by 10 again, and I get 100 watts. Well, that's another 10 decibel difference, right? Another 10 decibel increase. So now I've gone up 10 decibels twice. And now I'm at 20 decibels. So 100 watts is 20 decibels louder or more than 1 watt. I take that 100 watts, multiply it by 10 again. Now I'm at 1,000 watts. Multiply by 10, you get 10 dB more. So now I'm at 30 decibels. 30 decibels, so 1,000 watts is 30 decibels more than 1 watt. I multiply by 10 again, I get 10,000 watts, another 10 dB increase. Now I'm at 40 decibels. So 10,000 watts is 40 decibels more than 1 watt. Now notice that a 10,000 watt difference here gave me 10 dB increase. But if I just jump another 10,000, all I've done is doubled the number, right? So I've gone from 10,000 to 20,000. So I've doubled it. That's only 3 decibel difference. So where 1,000 to 10,000, a 10,000 difference gets me 10 dB, going from 10,000 to 20,000 only gets me 3 dB because I've doubled it. Okay? So now I'm at 43 decibels. So 20,000 watts is 43 decibels more than 1 watt. So this is that 3 and 10 rule. You can see that the differences in watts are huge, but the differences in decibel are not as huge. This is how decibels allow us to take a huge range and collapse it down to a small range. And a small range is easier for us to work with. Okay? I'd much rather deal with values of 0 to 43 than values of 1 to 20,000. Think about that on a knob. Okay? A knob that ranges from 1 to 20,000, that you could pinch with your finger. How could you possibly be very precise with that? Okay? So it's much better for us if we can collapse this down into something that we could actually screen print on a knob. Okay? Everybody with me so far?
Yes.
All right. So let's see. What is next? Okay. So here now I've drawn up a chart here that just goes from 0 to 10 decibels in 1 decibel increments, and showing kind of how this lays out if I start with 1 watt equaling 0 dB. Okay, so 1 dB would be 1.25 watts, 2 dB would be 1.6 watts, 3 dB, you ought to be able to figure this one out, is 2 watts, because it's a doubling, right? From 1 watt to 2 watts, I've multiplied by 2, that would be 3 dB more. Okay, so on and so forth. Now what's interesting about this is you could use this chart to do a lot of decibel conversions just kind of in your head. Let me demonstrate. So if I asked you what power level, and what I mean is in decibels, is represented by 80 watts. Well, we know that 8 watts is equal to 9 dB, right? So 8 watts equals 9 dB. And 80 watts is 10 times more than 8, right? So 80 watts would give me, would be 10 dB more than 8 watts. right? Because I know if I multiply by 10, I get a 10 dB increase. Okay, so if 8 watts is 9 dB and 80 watts is 10 dB more than 9, then 80 watts is 19 dB. See how that works? So you can use this kind of a chart to figure out most values simply by figuring out, okay, what's the first number that could fit into here that would work on the chart, and then you use the 3 and 10 rule to get you the rest. Okay? Let's try another one. Oops. What power level is represented by 1 milliwatt? Okay. 1 milliwatt is 0.001 watts, right? Okay, so let's walk this back from 1. So if 1 watt equals 0, okay, then we know that multiplying by 10 would increase 10 dB, while dividing by 10 would decrease 10 dB, right? So if I take 1 divided by 10, I would end up with 0.1. Oops. So 0.1 watts now. And that's a 10 dB decrease, right? Difference, between 10 is 10. So now I'm at minus 10. I divide this by 10 again, and I get 0.01. That's another 10 dB difference, right? So now I'm minus 20 dB. I divide by 10 again, and I get 0.001 watts. There's my milliwatt, right? And that's another 10 dB decrease because I divided by 10. So now I'm minus 30 dB, and that's my answer. So 1 milliwatt equals minus 30 dB if 1 watt equals 0 dB. Gotcha. Or you could say 1 milliwatt is 30 dB less than 1 watt. Okay? So let me clear that out. Everybody remember that answer because we're going to need it right now. So given now what we know about milliwatt, how many dB would be 4 milliwatts?
Minus 24.
So we know that 1 milliwatt equals minus 30 dB. Okay, so there's our starting point. 4 milliwatts. Wait, I forgot a 0 there, didn't I? So if I just double it, right? So I go to from 1 milliwatt to 2 milliwatts. That's a 3 dB increase. So what would be minus 30 plus 3?
Minus 27.
Yeah, right? So that would be minus 27. Double it again. There's my 4 milliwatts. That's another 3 dB increase. So what's minus 27 plus 3? Minus 24. Now you could also just do a shortcut and say, well, from 1 to 4 is 6 dB increase. And I could say, what's 30? Minus 30 plus 6. And I'd get the minus 24 as well.
Where did the minus 27 come from?
Because when I go from 1 milliwatt to 2 milliwatts, that's a doubling,
right?
And which would be 3 dB increase in value. So if I start with minus 30, 3 dB greater than minus 30 is actually minus 27.
And so when you're doing these, you're not adding the number like on the chart, you're adding 3 or you're multiplying 10 to, I'm just getting confused about, because there's the numbers that the watts represent on the chart, but you're not using those numbers, you're using 3 or 10 to get your calculation.
Yeah, so what I'm just showing you that ultimately there's that 3 and 10 rule, that doubling is a 3 dB difference, multiplying by 10 is a 10 dB difference. Using that, you get this sort of a chart. So I'm just saying that you can do it a couple different ways. So in this case, I can do it without even the chart at all, just knowing that every time I double it, I get 3 dB increase.
Okay.
Or I could look at the chart and see that, well, from 1 to 4, that's a 6 dB difference. So I could just take minus 30 plus 6, and I get minus 24. There's a couple. So there's more than one way to sort this out.
Okay.
Okay. All right. Now that we've sort of like tested the waters here, let's really see if we've got it. Okay. So let's rebuild this chart now using the 3 and 10 rule. Okay. So we're going to not use our calculators. If you wrote down those numbers, don't look at them in your notes. Let's just see if we can figure this out. Okay. We have to start somewhere, and let's start with 1 watt equaling 0 dB. Okay. So what values could we start plugging in here using the 3 and 10 rule?
3, 6, 9, and 10.
Yeah, so we know that 10 dB would be 10 watts, right? Because a 10, multiply a power by 10, and you get a 10 dB increase. So we would know that 10 and 10 would line up there, right? We could figure out 3 dB because we could just double the 1, right? 1 times 2 is a 3 dB increase, so that would be 2 watts, right? We could double that number again. We'd get another 3 dB increase. So 2 times 2 is 4. That would be 6 dB, so that would be 4 watts. Okay? I could take that number again. 4 times 2 is 8. And if I double a power, I get a 3 dB increase. So 3 dB more than 6 dB is 9. So that's where my 8 would go. OK, so far I've just said, using just the 3 and 10 rule, I've said, all right, 1 watt times 10 is 10 dB. Because that's the 10 part of the 3 and 10 rule. And then I can take this 1 and I can just keep doubling it. And every time I double it, it's a 3 dB increase. And that's how I can figure out 3 dB, 6 dB, and 9 dB. OK, so everybody understand how we got there?
No.
This is going to get trickier in just a second.
Okay, so we're doing 1 times 2 is
Yes.
2. And how do we get to 3 with that?
Because you double a power and you get a 3 dB increase.
So it's just that no matter what, like
Yes.
3.
That is
It's always
you
3.
have to, that is just a rule you have to accept.
Okay.
You double a power, you get a 3 dB increase.
Okay. And then how did we get to the 10 here?
Because the other part of the 3 and 10 rule is if you multiply a power by 10, you get a 10 dB increase. So I took 1, I multiplied it by 10, and I get 10, right? 1 times 10 is 10.
Okay.
And if 0 dB corresponds with 1 watt, 10 dB would correspond with 10 watts.
So I guess what I'm confused about is, so we did 1 times 10 to get the 10.
Yep.
Do we do that only because I don't understand why we didn't do 2 times 10 to get, like,
Because
it's not on the chart?
yeah, it's not on the chart.
Okay. So we're just doing what we need to do to get these numbers.
Yes.
Okay.
That's all I'm trying to do. I'm trying to fill in all of these blanks. Okay, so how can we figure out the rest of these now? Using only the 3 and 10 rule.
I mean, I would say like with increasing increments of like thirds, but
That doesn't quite work.
Yeah, that
once you
wasn't-
get past 3 dB.
yeah, that wasn't how it was there.
But
Yeah.
it would work for a 1 dB increase and a 2 dB increase.
We don't know how to do 1 dB or 2 dB increases. We only know how to do 3 dB increases or 10 dB increases. That's the only thing I've taught you to do.
No.
There's 1.25 and 1.5. I think I remember seeing it, but like that's just
Yeah, but we have to
knowing
calculate
why
that.
it works.
So I've taught you how to do 3 dB increases and 10 dB increases. I've also taught you how to do 3 dB decreases and 10 dB decreases, haven't I? So there's a clue.
10 to 7.
Ah, yes. So if I take that 10, divide that by 2, that's a 3 dB decrease, right? So in the same way, if you double a power, you get a 3 dB increase. If you divide a power in half, you get a 3 dB decrease. Right? If you multiply it by 2, you go up 3 dB. If you divide it by 2, you go down 3 dB. So if I take that 10 watts, divide that by 2, that would be a 3 dB decrease. So what would be 3 dB less than 10? 7, right? So that would be, I would put a 5 there. Because 10 divided by 2 is 5. 5 watts equals 7 dB. Now what could I do? I could take that 5 and divide that by 2. So 5 divided by 2 is 2.5. That would be 3 dB less again. So be 4 dB, right? 6, 5, 4. So 2.5 goes there. Okay? Can I do any more? Yep. Yeah, so I've got another 3 dB jump here, right? From 4 to 1. So what would be 2.5 divided by 2? 1.25. Yes? Yep. 1.25. And if you can't do that kind of conversion in your head, you can do that in that part in your calculator. Okay? All right, I've got 3 more slots here I have to fill. How can I fill them?
By getting it close enough and then rounding so we don't get big, gross, messy numbers.
No. You have to use the 3 and 10 rule. Anybody? It's very rare that someone's able to figure this out without me giving him a hint. So.
Now you can't tell us it.
This is the rest of the class. Is just trying to figure this out.
We got another 50 minutes to figure this out.
It's like a video game being like, want to lower the difficulty?
That's right.
It's like, no. Never beat this level. I'm going to play it at this
So would the solution be start at 20 dB and go down in 3 dB increments?
Let's try it. So you're saying 20 dB. Yep. What power level would be equal 20 dB?
It would be
20 watts. Yep.
What's that?
20 watts. Right? No.
It's an 11 watt. No.
If I have a 10 dB, then it's going to be 100 watts.
Yeah, so 100 watts, right? If I take 10 times 10 is 100. Yep. That would be a 10 dB increase. So 10 dB plus 10 dB is 20 dB. So yes, 100 watts is equal to 20 dB.
Yep.
Does that help us at all? Let's try. What?
So then if we go down 6, and we can get to 8. Yep.
So how could we do it? So walk me through it.
We go down 3 dB at a time.
So what's 1 divided by 2?
50.
50 watts. That would be 3 dB less than 20, right? So that would be 17 dB.
14 would be 25.
So I could take that 50, divide that by 2 again. 25. That would be 3 dB less again. I divide it by 2, I get 3 dB less. So 17 less 3? 14 dB. Okay.
11 dB.
25 divided by 2 is?
12.25. 12.5.
12.5?
Yep.
Okay.
11 dB.
That would be 3 less than 14, right? So that would be 11 dB. Oh, we're getting close. We're getting now towards our chart here. We divide it by 2 again. We get 6.25. There's our 8. Look at that. 3 less than 11 is 8. So this would be 6.25 for 8. Yes? All right. Let's keep going. 6.25 divided by 2. If you need to break out your calculator for this part, that's okay. That would be 8 minus 3. That's your 5, right? So this is 3.125. And then our last one
is 1.5625, which is
1.6 is pretty rounded.
Yeah.
we could say 1.56 or or 1.6, which is I think what the chart originally said.
Yes.
It's the same thing either way. So this is the cool thing about decibels is close counts.
Okay, so we did. Right?
Okay, so you can be super sloppy with your math when you're working with decibels, and you will still get the right answer. Okay, it's incredibly forgiving. So yeah, we could put 1.56 or 1.6 in here, and it would both ways it would work out to be 2 dB. Okay, so 1.6. There we go. We did it. Should we check our answer here? Oops, over here. 1, 1.25, 1.6, 2, 2.5, 3 point. Well, so this said 1.5, right, on the original chart. So we got 3.125, but it's the same thing.
Oh, yeah.
Both 3.15 and 3.125 both collapse into 5 dB. So this is what I mean, close counts. Okay. 4, 5, 6. So this was 6.25 that we got, and the original was 6.3. But again, it's the same thing. When you're working in decibels, close counts. 8 and 10. It works. We did it. So just to think about it for a moment, we kind of overshot a little bit. It would have been a little bit quicker to just take our 1.25, multiply that by 10.
Yeah.
Right? So that would be 12.5, and that would be 10 dB more than 1. Right? So there's your 11 dB, which was right there. And then we could have just walked straight down.
If you were starting at 1.25, but we didn't have 1.25 yet.
Oh, that's right. We didn't have it. So we could have done. Where's the other one? I forget. There's another one that you can do.
Doubled 7. That's what you're looking for.
Yeah, 7. We could have doubled.
7 to get you
Yep,
14
that's what it was.
down.
Yeah. So we could have taken that.
Now we just have more information.
Yeah.
Just
Just a longer chart.
That's right. But we got it. There's a few ways to. But yes, to figure those last few out, you have to kind of go outside of the bounds of the chart, right? In order to walk yourself back in 3 dB increments, because you only get one 10 dB hop before you've left the chart. Okay.
The 9-dot experiment, where it's like,
Yeah.
you got to get outside the box to actually solve.
Okay. So that's just an interesting little exercise. I would not read too much into this. The point here that we're trying to make here is to drive home this notion of the 3 and 10 rule. Okay? That's the part I want you to remember. I don't necessarily need you to remember this chart. I don't need you to remember all of the little steps we went through here. But what I need you to remember is that when you double a power, you get a 3 dB increase. When you multiply a power by 10, you get a 10 dB increase.
And wait, when you say, okay, double, are you saying number times 2?
Yes.
Okay. So.
Likewise, if you take a power and divide it by 2 or halve it, you get a 3 dB decrease. If you take a power, divide it by 10, or 1/10 of a power, is a 10 dB decrease.
But and
Okay.
you always have to, I think maybe what I'm getting confused with is you always have to start from something.
Yes.
You have to have something.
Yes, you have to have something. This is how decibels work. They compare things. Decibels are do not represent an actual value.
It's all relative.
It's relative. What's that? Divide a power by 2. Okay? So, yes, decibels are a comparison. 3 decibels, if I just say, well, that's 3 decibels. Well, 3 decibels more than what? Right? Because 3 decibels is not an actual value. 3 decibels tells me that just means it's different. 3 decibels different. 3 decibels different than what? Okay? It could be 3 decibels more loudspeaker boxes. Right? If I have 2 subwoofer cabinets and then I go to 4 subwoofer cabinets, I have 3 decibels more subwoofer cabinets. Right? It doesn't have, it's just a difference between 2 things. Could be in dogs. Right? If I go from 1 dog to 4 dogs, I have 6 decibels more dogs than I had before because I doubled my number of dogs twice. Okay? It's just
So is it just like decibels helps us understand that an increase is happening, but we're not worrying about like the, for lack of a better word, like the big number reality of the situation?
Yes.
We're just trying
it's
to
a shorthand.
Okay.
It's a shorthand.
Okay.
Because I don't really want to know that, I went from 1,538 to 87,127. Like, that's not particularly helpful to me, and that's difficult for me to remember. Right? But it's much more easy for me to remember, well, I went up like 36 dB. So I got 36 dB louder than wherever I was before. I don't particularly care where I was before. I just know that I'm 36 dB louder than that now. Right? And so think about this in practical terms of, okay, I am going to turn a knob because I need it louder. How much do I turn it up? I'm not going to say, turn it up by, 76,782, right? I'm just going to say, give me another 20 dB. Right? That, I don't really care where it is right now. Just 20 more dB.
And then when you increase it, you technically don't, you increased it, but like technically if you're going to increase it more, what you just increased it to, you don't really care what that was.
No.
So it's just like a way of saying like turn this up or turn this down.
It's a difference. It's a shorthand difference. Okay? So I can't say, set it to this value because I have no idea what the value I need it to be is. I just need it to be a certain amount more than that.
Yeah.
And rather than saying some value more that has so many zeros at the end of it, it's easier for me to just use a shorthand called decibels. Okay?
It just seems silly because it's like, basically it's like we have this so we don't say turn that up a little bit or turn that down a little bit.
Well,
like
it becomes meaningful though when you start examining the science of decibels. Okay, so you have to understand what different decibel differences are perceived by us. For example, most average normal human beings that have not sat in a single golden ear session, the smallest difference in level that they can perceive is 3 decibels. So you do a 3 decibel difference and they can just barely perceive that anything changed. Okay? You turn it up 2 decibels, they will think nothing happened. Most average people will say you didn't change it at all. Okay? Now, if you do some ear training, you can train yourself to hear 1 decibel differences. Like it is possible for us to do that, but it takes practice and training. But your average person needs 3 dB. So knowing that, you would then know that, well, if I'm going to turn something up or down, I have to do it by at least 3 dB or no one's going to notice. But 3 dB is doubling it. Right? So in order to increase it by the smallest amount that anyone could even notice, you have to double it at the power level. So think about that in terms of power amplifiers. So if you are currently driving your loudspeaker with a 1,000 watt power amplifier, and everything's turned to 11 and you're maxed out, and you want it a little bit louder,
You have to double it.
you have to go at least to a 2,000 watt amplifier to make the smallest difference that anyone could even perceive.
And if you go up 10 dB, that means that
10,000 watts.
10 times
Right?
louder
Yeah.
than what it was
Yes.
before.
Yes.
Huh. Okay.
Okay? So that's where this becomes helpful, right? If you understand that there are thresholds to our perception, and you have to be conscious of that. So if I say, well, I'm going to take my 1,000 watt amplifier, I'm going to go to a 2,000 watt amplifier. That'll be better. It's like, well, yeah, you're going to spend a whole lot of money to barely make a difference that anyone could hear. Okay? So that's how decibels can help us. So let's try some of these with our calculator. Okay? So how much louder is 700 watts than 63 watts? Okay, so remember, to figure this, the actual formula for this, if you're going to plug it into your calculator, is decibels equals, power decibels anyway, equals 10 times the log, and this, by the way, this is a base 10 logarithm. which is usually, if you only have one logarithm button on your calculator, it's probably a base 10. But there are some calculators that will have more than one logarithm button. And if you do, you want to look for the one that has the little 10 next to it. Okay? So how much louder is 700 watts than 63 watts? This would be 10 times the log of, remember, 1 power divided by the other power. So 700 divided by 63. Not 36. 63. Okay? That's the formula. 10 times the log, 700 divided by 63. So if we do that on the calculator, so here's my calculator, okay? And I'm going to say, the way that I would do this on pCalc, your calculator might be different, but I'm going to first do that division, that 700 divided by 63. That's what I'll do first. So 700, oops, not 1,000, 100. 700 divided by 63 gives me 11.11111111. And then I'm just going to see I've got more than one log button there. So I want the log 10. So log 10, and then times 10, and I get 10.46 dB.
I don't have any of that log stuff.
You got to turn that on.
We can deal with that later.
So
if you
no,
want.
go to View, Display. Oh, wait a minute. Go to Layout, and Basic maybe? No, Large. No, sorry. View. Sorry, it is Layout. So go to Layout, Regular Large.
Oh,
No, where it says
sorry,
Large.
sorry. Layout,
Large.
large.
There you go.
Okay.
Log 10. Okay? So 10 times the log of 700 divided by 63, I get 10.46 dB. Okay? So 700 watts is 10.5 decibels more than 63 watts. That's all that means. It doesn't mean 700 watts is 10.5 dB.
That much more.
It means 700 watts is 10.5 dB more than 63. Okay? You understand the difference? Okay. Decibels are not actual values. They are relative values. Okay. So let's try another one of these. I need to get rid of these animations. Okay. How much louder is 10,000 watts than 3,000 watts? Okay, so to figure this out, it's some decibel value, and that's going to equal 10 times the log of 10,000 divided by 3,000. Right? Okay, so let's do that on the calculator.
We do the 10,000.
That's what I would do, is 10,000 divided by 3,000. I do that part first. So 10,000 divided by 3,000 equals, if you've got a real fancy calculator, you can probably plug that whole formula in and it will just do it.
My other
But
calculator does
I really don't like that, because when we get into more complicated problems here,
Use parentheses correctly so you
Yeah.
stay in order of operation.
yeah. But the reason I don't like that is sometimes, as you'll see in some of these, when we get to some more complicated problems, it's sometimes helpful to see the steps.
Yeah, can you show
Okay.
me later how to make that come up?
Oh, the tape?
Yeah.
Yeah, it's just in your, go to View, and then Show Tape.
Show tape.
And it'll just show
I
you.
kind of like that.
It'll just show you all the things you've done since you last. There's
Go
a
to View.
View menu, and say Show Tape under View.
Under view.
Oh, you've got the older version. Hit that little button called Tape. There you go. Okay. Okay, so 10,000 divided by 3,000 is 3.33333333, right? So then I'll say, all right, give me a base 10 logarithm of that. So I'll hit my log 10 button. I get 0.52287875453. and then I say times 10, and I get 5.23 dB.
So sorry, so you got the 333. You did the log 10.
Then
Times
and then times 10,
okay.
right? Because it's 10 times the log of
Oh,
1
okay,
divided by
okay,
the
okay.
other, right?
Yeah.
So there's the whole steps. I did 10,000 divided by 3,000, and then got that answer. And that answer, I got the logarithm of that, and then I multiplied that logarithm by 10. And I get 5.23 dB. So 10,000 watts is 5.23 dB louder than 3,000 watts. Okay? 10,000 watts is not 5.23 dB. It is 5.23 dB more than 3,000. Okay? Okay, let's try another one of these. All right, here's sort of maybe a real life situation. You're going to go buy an amplifier. And for whatever reason, you think you want an 800 watt amplifier, or the person at Best Buy is trying to convince you to buy an 800 watt amplifier. But there's a 350 watt amplifier over next to it that's quite a bit less money, and that fits your budget. So the question here is, well, how much actual volume or loudness am I going to sacrifice if I buy the smaller amplifier? Right? Like, is this worth the money? Should I go back and save for another couple weeks so I can come back and buy the 800 watt one, or should I just buy this 350? Well, this is assuming all the rest of the things are equal. Like, you're going to use the same speakers with both amplifiers, so you're not changing anything else. It's really just one amplifier over the other, but everything else is the same. Then to figure this out, it would be, so what I want to know really is how much quieter is that 350 watts?
How many decibels quiet?
Yeah.
Okay.
Because
How many decibels
because I
quiet?
know that like 3 dB is the smallest that most people could even hear, right? So
if it's less than, I don't really care.
Yeah.
Okay.
Right. Okay. So this would be 10 times the log of. Now here's the thing. How do you decide which number goes on top and which number goes on the bottom? Depends on if you want a negative number or a positive number in decibel difference. Okay. If you want a positive decibel value, you put the big number on top. If you want a negative decibel value, you put the little number on top. Okay. In this case, I want a negative decibel value because I want to know how much quieter my 350 watt amplifier will be.
Sorry, can you just say all of that one more time so I can?
Okay. So the actual formula is P0 divided by P1, right? So one power divided by the other power. Well, I've got two powers here, 800 and 350. How do I decide which one's P0 and which one's P1? It just depends on what sort of value I want. Do I want a positive value for decibels? If I do, I put the big number on top, right? So the 800 would go on top. If I want a negative number in decibels, then I would put the small number on top. Okay? So in this case, I want a negative value. I want to know how much quieter is this 350 watt amplifier. So I would do 350 divided by 800. Okay? And that will ultimately give me a negative value in decibels. So let's give this a shot, shall we? Come on. So 350 divided by 800 equals 0.4375. I'll get a logarithm of that. I get negative 0.35 times 10, and we get,
3.59.
yeah, that's what I got too. So it is just barely over a 3 dB difference.
So
Okay.
fair, right?
Yeah, I'm like, well, like if this is for my living room, my kids are not going to hear the difference between that. Right?
Yeah.
So who cares? Why? I'm just going to get the smaller amplifier. Big deal. There's barely any difference I could hear. Okay? All right. Let's see. Where are we now? Everybody with me?
Yes.
Okay.
I can confidently say that. For the first time.
There we go. Okay, let's talk about doing this backwards now.
Oh, hold on. I have one question.
Yeah.
Why 10? Why
What?
are we using the 10 in the equation?
Just because the logarithm, the logarithm all by itself doesn't quite give us a usable range. So if we multiply it by 10, we just get easier numbers to work with.
Okay.
It's,
I can accept that.
yeah. There's a lot of things about sound and a lot of things, particularly about decibels, that you just, yeah, we're just basically moving to decimal place. Yeah. So, but there's a lot of things about sound, particularly in this section about decibels, that it's just like,
Okay.
I can't justify it. It just is, right?
What did you say about deci?
Deci, the prefix, like if you're looking at metric, you start at like a meter. A decimeter would be 10 times that, so you would move the decimal place one place, or if you go backwards, things like centimeter, millimeter, they're just prefixes.
Okay.
So we're, yeah,
Deci
by
is
multiplying by 10, we just move the dot, the decimal,
Okay.
one spot, and it just gives us a better number.
But I can just like accept
Yeah.
that and not worry about
Yeah.
why it is. Okay.
Absolutely.
I'm good.
And there's a whole lot of that kind of stuff that I'm going to throw at you this section. It's
I'm
just
okay
like,
with
look,
that.
I can't explain it. It just is, right? There's a lot of things like that about sound that we have invented a lot of things in sound that help us talk about it. And those words and values and units of measurement we've invented are only meaningful if we all agree that they are, right?
Yeah.
So it's like you just have to be okay with that or you can't do sound for a living.
That's why I
right?
think the decibel thing is silly, just because, like, I mean, obviously it's extremely important,
Right.
but it's just like, we need to make this thing up so this can make sense and
Yeah.
exist and be real, even though it's...
That's all it really
it's
is
not a weird thing.
is we just made it up, okay? We made this thing up, and it works. It helps, we're fine with it as long as we all agree that it works,
thing, yeah.
right? If we all agree that, okay, yes, we can work like this, then it's like everyone either has to agree to work in metric or not, right? It doesn't work if half the people are not agreeing to use it, okay? That's how decibels work too. You just kind of have to say, all right, I'll just buy into that, okay? Now let's do it backwards now. What if you know the decibel difference and you want to convert that back into the actual power level? Okay, that might be useful. Maybe there, and I'll give you some examples in a moment of why you might want to do that. To do this, you figure out what's called the power ratio. And the power ratio equals 10 to the power of the decibel value divided by 10. Okay?
Oh, that's important to know.
Yes, you should absolutely write that down. So let's take a look at how you would figure this out. So if I asked you, what is the power ratio of a 13 dB level difference? So what's the power ratio of 13 dB? Well, to figure that out, I would have to do 10 to the power of 13 divided by 10. Okay? You see that? So let me show you how you'd figure that out using my favorite calculator. So the first thing I'm going to do is 13. Oh, why does it think I've got a pen? Stop it. I don't have a pen. Oh, let's see. Okay. So 13. Oh my goodness. Okay. 13 divided by 10. That's the first thing I'm going to do. And I get 1.3. All right? And then all I've got to do is there's this little button on the calculator that says 10 to the power of x. Okay? And it's right under, in my case, right under my base 10 logarithm. So if I hit that button, it's going to do 10 to the power of whatever number is currently showing on my calculator. So if I just hit I've got that 1.3, which is, that's 13 divided by 10. So I just hit 10 to the x, and I get 19.95. So 19.95 is the power ratio of 13 dB. Okay? Now, if I want to find out, so what would I do with this? Let me get my next little thing. So, knowing that 13 dB equals 19.95 for a power ratio. Knowing that, if I then ask you, you have a 300 watt amplifier and you need 13 dB more volume, how much more power do you need? So how much power would you need to get 13 dB more sound? Okay? Well, all you have to do is take your 300 watts that you currently have and multiply that by the power ratio of 13 dB. So 19.95 is the power ratio of 13 dB. So you can take any value in watts, multiply it by 19.95, and you will have a number of watts that is 13 dB more than you had before.
Because that kind of functions the inverse of
Yeah.
a logarithm, right?
How can we choose any number of watts?
Whatever number of watts you currently have. And I'm saying we currently have 300.
So if
Okay.
you get the second problem, if you start with 300 watts, wants to go up 13.
Yep.
If you get that first,
Yeah.
do you just
Well, then I have to first figure out the power ratio of 13 dB.
so you just take however much you want to go up and
Yeah.
do
Yep.
the first problem?
Yep.
Okay.
So I could do the same thing with 15 dB or 18 dB or 20 dB or whatever. I would just say 10 to the power of that dB divided by 10. I would get some sort of a number that I would then multiply the current power I have. So in this case, I have 300 watts. I'm going to multiply that by 19.95. Someone want to do that? What's 300 times 19.95?
5,985.
That's what I got. Did anyone else get that?
Wait. No, I didn't. Maybe I just didn't know. What, it's
300 times 19.95.
Okay, yeah, I did something.
Okay.
I got that now.
So what this means is that 5,985 watts is 13 dB more than 300 watts. 300 times 19.95? No, 300. One more zero.
Oh, shoot, okay.
Okay, you've got to do an all clear. You've got extra numbers in there that are hit the AC. Clear this calculator out completely. It was piggybacking other old numbers off of you. So now do 300 times 19.95.
Yesterday, I decided I'm gonna rearrange my entire room by myself. There's not much room to rearrange and shift everything, so
You hit the point where
There you go.
Yes.
Okay. All right. So what we've now learned is that 5,985 watts is 3,000 or is 13 dB more than 300 watts. Okay? So let's just prove this now. Let's prove that that is true. Let's work it now back forwards again. So if I just take, I've got two different values in watts, right? I've got 5,985 and 300. What's the dB difference between those two things?
Okay, so it's 10 log
Yep.
divided by
10 times the log of,
5985
yep,
divided by 300.
yep.
And we're getting a positive number, so we put the big number on top.
Yep.
Okay.
So what is this?
So 5985 divided by 300
Yeah,
exactly what you typed.
equals this. And then I do the log 10, and then I do times 10. I got 12.99.
Yeah.
that's 13 dB, isn't it?
Yeah. Oh, hey, it is. But it's
Right.
not the same as 13 dB, but it's forgiving, so it's still the same.
Yeah,
in the count.
'cause remember,
Because none of
We
them
could
agree on
know,
what it is.
even I, who have been through golden ears, 20 20 times at least could not hear the difference between 13 dB and 12.99 dB.
Yeah.
Right?
So at very high volumes, I know that the math stays identical,
Yeah.
but to your ears, a 3 dB increase at much higher volumes is much more apparent than at lower volumes, or is that
No.
not so much just because your ears are?
No, it sounds the same.
It's gonna be okay.
3 dB sounds like 3 dB, whether it's you're going from 1 watt to 2 watts or 10,000 watts to 20,000 watts. Still sounds like it's the same difference.
Okay.
It's an interesting thing about our hearing system.
I had no idea that dB wasn't like. I know it's real, but like that's the way that I'm thinking of it. I was like so concerned about like what dB was, and it's just like this
Well,
is it.
now you know.
It's like not really as complicated as it seems.
No, it's not.
Are we gonna
Okay.
In this class, are we going to get into the various different types of decibel, like where they fall into?
We will.
Okay, great.
Give me a couple more days, and we'll get there. Those are called reference levels, by the way.
Okay.
And we'll talk about that in a minute. Okay, so, all right, so here's like a real deal situation that you might find yourself in. And we now have all the skills to figure this out. So I have a loudspeaker, and it puts out 60 decibels with 2 watts of power. And you just accept that for now, okay? We don't need to know what 60 decibels more than what. Just accept that as the 60 decibels more than something, okay? 60 decibels it's just standing in here for 0 decibels or 1 decibel or whatever, right? But I would like it to put out 98 decibels compared to 60 decibels, okay? So how much power would I need to do that? Okay? In other words, I got to go buy an amplifier. How big does this amplifier need to be? The first thing I want to find out is what is the dB difference here that I'm dealing with? Okay, so I just say I want to do 98 decibels. I'm already creating 60 of those. Okay? So I can just subtract that out because I don't have to make those. I'm already making them. It took me 2 watts, and I've got 60 decibels more than 0. Okay? So 98 minus 60 gives me what? 38. So I'm looking at a 38 decibel difference. Did everyone else get that? Get 38? Yes? You with me? Okay. So 38 decibel difference. I need to know the power ratio of 38 decibels, don't I? So that's going to be 10 to the power of 38 divided by 10. Whoops. Lost my marker there. Okay, so what is 10 to the power of 38 divided by 10?
6,309.57.
Okay, I have 2 people that got that. Did anyone else get that? I need 1 more person or it's not right.
Yeah.
Okay, great. Okay, so that is the power ratio of 38 dB. Is that the answer? No.
Because we want to know how much power we need.
Yeah, so
And
I
that's
need,
the power
and I already have 2 watts. So I need to multiply. If I want,
What unit is your power ratio in? What?
Because what is it? It's
It's
that
a
number to
ratio.
1, right? Like
Yeah.
that's
So it'd
what
be
that represents.
basically
Okay.
the ratio, the other half of that ratio is whatever value you started with.
Okay. Great.
In this case, I started with 2 watts,
Great.
right? So it would basically be this times the 2 watts I already have
Okay.
will get me the number of watts I would need to be 38 dB more than what I have at the moment. Okay, so 6,900 or 6,309.57 times 2.
12,619.1468.
Yep.
Point what?
14.
1.5.
We'll say 1.5. There you go. Okay. So I would need upwards of a 12,000, 13,000 watt amplifier to pull this off. Probably not super practical. There aren't a whole lot of those out there. I think we might have one in the shop that, with the right power supply and all the right circuit, but we might maybe get close to that. So, you know, this would tell me, all right, I'm tackling this problem from the wrong direction. Right? Adding more power is not going to get me where I want because I can't go buy a 12,500 watt amplifier. So in reality, what I need is I need a loudspeaker that can do more with less power.
Can you do so I get all the math and like I get how that works.
Yep.
But if I was like alone and read this problem, I would be like, I don't understand what this is asking me. So what's your like? How do you do that?
So loudspeaker puts out whatever it puts out, right? And so that, you know, we haven't talked about this yet, but you can measure pressure levels as decibels as well. Okay, so that's all I'm saying is there is some pressure level that we are calling 60 decibels at the moment. Okay, and at the moment I know my amplifier is putting out 2 watts. It's a little cheap, tiny, dinky amplifier that's probably running on a 9-volt battery or something. Okay, and it's putting out 2 watts, and I'm getting 60 decibels worth of pressure on my meter, and that's not enough. It's not loud enough. It doesn't sound loud enough to me. I need it to be louder, and I'm saying, well, it's got to be, I need like almost 40 dB louder than this because I'm gonna, you know, do an explosion or something in my show. And so what do I got to do? I need to go get a bigger amplifier than this little dinky, you know, Radio Shack one that I built myself. Okay, so how big of an amplifier do I need to buy in order to get this loudspeaker to put out the amount of sound I need?
Okay.
That's the question I'm asking.
Okay.
Now,
so you're like, I have 60 dB. I need 98.
Yes.
This amplifier is not going to do that for me.
yes,
What kind of amplifier do I need to
Yes.
be able to get that?
exactly. And what we found out is it's a 12,500 watt amplifier that would get us what we need. Now, odds are my little loudspeaker is probably going to jump out of the box if I hit it with 12,500 watts. So that tells me that the problem is less with my 9-volt amplifier than it is with my horribly inefficient loudspeaker. And I'd be much better to find a loudspeaker that was just a bit more sensitive. Okay. So before I would want to do this math before I went out and bought anything, because I want to make sure I buy the right thing. And if I went out and bought an amplifier, I would not solve my problem. I would not get my 38 dB.
So when you're looking at this problem, when you look at this problem, what is the first question that you ask yourself that you need to figure out?
So the first question I ask myself is, how many more dB do I need? Right?
How many more dB do you need
Than what I already have.
currently?
Yeah.
Okay.
So that's the first thing I asked for.
Okay.
Right? I already have 60. I already know how to make 60.
Okay.
Okay? It takes me 2 watts. How much more do I need?
Okay.
So I want 98. I already have 60. So I only need to make 38 more.
Okay.
Right? So how do I make 38 more dB using power? Well, to do that, I would need to know the power ratio of 38 dB. So I figure that out, 10 to the power of 38 divided by 10. I get the power ratio. And then I just say, all right, any number that I multiply by 6,309 will be a number that is 38 dB more than what I started with. So if I multiply 15 by 6,309, I will get a number that is 38 dB more than 15.
Okay.
Right? In this case, I'm starting with 2 watts. So I just take 2 watts times 6,309, and I get a number that is 38 dB more than 2 watts,
Okay.
which just happens to be 12,620 something watts, right?
Okay.
So your power is a ratio, so it becomes a constant ratio.
Yeah.
Okay.
So you could make yourself a chart that says, anytime I need 38 more dB, I just multiply however many watts I have by this number, and I will get an amount of watts that is 38 dB more than that. Okay? So you could just make yourself a little cheat sheet and said,
Or you can just
power ratio of 6 dB is blah.
you can remember 3 numbers.
Yeah, or you can just remember the formula and do it, right? It's not that tough, right? It gets more complicated than this when we start really looking at multiple steps of, okay, well, we'll get into this on Monday, but we know that sound propagates through the air in a certain way, and we haven't accounted for that here. We haven't accounted for the sensitivity of the loudspeaker. We haven't accounted for how much level we're feeding into the amplifier to begin with. So these are all variables that would contribute to this problem. And by the end of this, by 2 weeks or so from now, we will be considering all of those variables all at the same time, because you have to. Because as we can see, if we only consider watts, the solution is not practical.
Right.
We have to consider watts and pressure and voltage and efficiency and all of those things all at the same time if we're going to really tackle this problem in a realistic way.
So, sorry, one more thing. When you do, you do the 10 to the power,
Yep.
and you get this number, and you multiply that by whatever watts you already have?
Yep.
Okay.
Whatever number of watts you already have.
Okay, got it.
Yep.
If it was like 17 or 85.
I can multiply by
just
17 or
do
85 or
that.
whatever.
That's the amount of amplitude you need, or
What's that?
that's the amount of amplitude you need, 156 watts.
Yeah, I mean, in this case, it's not amplitude specifically. I would just call it's the number of watts out of my power amplifier I need. So, and power amplifiers are specified this way. They'll say, well, this is a 10,000 watt amplifier. Or more specifically, it says this amplifier will put out 10,000 watts against an 8 ohm loudspeaker or an 8 ohm load. And it would do more than that against a 4 ohm load, right? But we'll get into that later as well. But the amplifiers are spec'd that way. They'll tell you how much power they put out for given scenarios. And in this case, if the only way to solve this problem for me is to buy a bigger amplifier, then I've got to buy a really big amplifier, a super big one that is going to be hard for me to find because there are not a lot of people that build and sell 12,500 watt amplifiers. They just don't exist. So
Get a better speaker.
yeah, that's
Getting more efficient speakers.
yes, that's the real answer to this. Is I need a loudspeaker that can make more sound with less power, right? That's what I really need. If I could somehow get, if I could get 80 decibels with only 1 watt, then I'd be in a much better situation, right?
Yeah.
And there are loudspeakers, it is not unheard of for an average loudspeaker that's not very big to put out 98 decibels with 1 watt of power 1 meter away. Like, that's possible. The engineering to pull that off exists. That's K50s are even more than that.
They
I mean,
put out like 100 or something at
Yeah.
1 watt.
it's quite a bit. So that's possible. Okay, let's see. I think that's it. So what we're going to do on Monday is look at how decibels work in pressure values. So this is anything that's a power works the way we've talked about today. But anything that works like a pressure or a force, really, anything that if you look at sound in any sort of force thing, which could be voltage, current, pressure, these are all forces, right? Then decibels work a little bit differently for forces, okay? So the math is different. So that's what we'll do on Monday, is we'll look at how do you calculate decibels when you're looking at it as a force as opposed to a power, okay? And the math is only a little bit different. It's mostly the same, but it's just basically, it's more or less everywhere you see a 10, make a 20 instead. That's the gist of it. But we'll go over that in more detail later. Okay, any other questions before we wrap this thing up? Yeah. So, in the syllabus are some reading things you can, if you want to read more about power decibels, I've given you some things you can read. That can show you some more examples of the math and things. And I sent you the worksheet yesterday.
So we should be able to do some of that now?
Yeah, there's probably a few things in there you could do.
Do we cover gain structure in this class?
I mean, not really. We talk about it a little bit, but not probably the way you're thinking.
It's kind of like the stuff that you can use, that like when you're making the gain structure, this is the math that if you want to figure out what you're
Right.
actually doing, this is.
Yeah. For example,
I understand like the fundamentals of an ideal gain structure. It's just
yeah.
take
No,
it-
so what we're doing in this class is we're teaching you the math where you could calculate
Okay.
your gain structure, but we're not necessarily going to the point of like, okay, Now, how does that translate into knobs I would turn on this equipment? We're not quite going to get there. We'll get there in another class.
That is which class?
Yeah,
Assuming like in classes rather than just like
right. Aside from doing in production, you would cover that in the electronics class, the theater audio electronics class, and a little bit in the sound system engineering class. Okay. Yeah. Okay. So go look at that homework now and see if there's any of those that look like things that you could do. I think there's probably a couple in there you could do with the information I've given you so far.
One and two for sure.
Yeah.
This one that says, what is your peak power handling? Is that?
You could probably figure that out. Yeah.
Okay. And then what are these ones that have 3 next to it?
Oh, sorry. That's just, I used to give like certain number of points for some of these questions.
Oh, okay.
And that's, so just ignore that. That was just a note to me saying this one's worth 3 points.
If a foreign electrical power connector produces 160 volts, how many dBV would that be?
Yeah, I haven't talked about that
Okay.
yet.
So just and are these like, I was very confused on the other worksheet just because I was confused about the whole thing. Do you like go from like what we talked about like chronologically on the worksheet, or is it just like
not necessarily. Yeah, not necessarily.
Yeah, so I think